Hello dear students, this is Dr. Aisha Nazuk here, and this is my second video for the course Introduction to Econometrics. So first of all, if you've still not subscribed to the channel Rao Hub, please subscribe to the channel, and to make sure that you keep learning not only statistics but other concepts of econometrics as well. You are more than welcome to explore all the playlists that are available here on my channel. Okay, so today's lecture is about two variable regression analysis, and this lecture is based on Gujarati and Porter. These are the actually author names of the book, Basic Econometrics, Gujarati and Porter, Chapter 2, 5th edition. You can easily download this book from the Genesis library. By the way, if you want, if someone wants that the instructor, that is me, Dr. Aisha Nazuk, if you want the book to be sent to you through an email, you can always reach me out. My email ID is mentioned on the last slide. So you can either take the video towards the end if you want to see my email ID, or watch the full video and then you'll see my email ID on your screen. Regarding the NUST students who are enrolled in BS Economics program, I've already uploaded a complete PDF file of this book on LMS portal. Okay, so without further ado, let's start today's lecture about two variable regression analysis, some basic ideas. Okay, so just a quick recap of the first lecture, in which we discussed the general purpose of regression. So regression analysis is largely concerned with estimating or predicting the mean value. So what does that mean? Whenever we talk about calculating things versus predicting things, so what is the difference? For example, if I give a statement to a person that, look, Mr. Ali, I have calculated that you behave in a particular manner whenever you are angry. If I use the word calculate, actually I'm implying that I'm 100% sure that Ali is going to behave this way. But what if I say that Ali, I have predicted that you behave a particular way whenever you are angry. So what's the difference? Now I'm saying when I use the word predict, that means generally or on average, whenever Ali is angry, he is behaving in a particular way. So that means regression is concerned with predicting the mean value or the expected value or the average value of the dependent variable. The example of Ali that I quoted, my dependent variable or my study variable was Ali's behavior. But in any other example, it could be any variable. I mean, if I want to predict, let's say, quantity demanded, then the regression will be predicting the average quantity demanded for a given value of price. Okay, so let's have a quick and easy example that will further strengthen the concept of regression. Let's say we have data of 60 families, right? In some hypothetical community, let's say we have data of 60 families, and what type of data we have? We have their weekly income and we have their weekly consumption expenditure, and both are, let's say, in dollars, right? So Y, or my dependent variable, is consumption, because I'm trying to predict people's consumption behavior based on their income. So consumption is a dependent variable, whereas income is independent variable. So let's say, before going further into this debate, which variable is dependent and which one is independent, let me first introduce the concept of population regression function, right? Which concept? Population regression function. Okay, so we have data of 60 families, and those 60 families are, let's say, divided into 10 income groups. So let me show the table that will make this further clear. So let's say we have data of, these are like the 60 families written inside the main body of the table. So this Y, which is our dependent variable, is consumption expenditure, whereas X is their income level. So these bold figures 80, 100, 120, so on, these are different these are different income values, right? So this is someone or a family whose income is 80, another family whose income is 100, and so on. But now let me step by step try to build the concept related to the population regression function. First of all, if you look at this data, what you are looking is, you must be wondering that why we have these 1, 2, 3, 4, 5 values here against this 80. So actually what this table is trying to show, that no matter if your income is 80, it's not necessary that each family will be spending same. For example, if this is family number 1, its income is 80, it's consuming 55. Another family, probably income again 80, but it's consuming 60. That it is fairly possible that at same value of income, the consumption patterns are different, and what we are expecting, that if on average I am able to predict predict the average consumption for this group, for example, then my end goal will be met. That is the end goal of regression. If you look, I have also calculated the average consumption values. For example, simply add these consumption figures, that is 55 plus 60 plus 65 plus 70 plus 75, and then divide by the number of observations here, which is 5. So if I add these values, divide by 5, I get 65. And what is that 65? That 65 is conditional mean or conditional expectation of consumption for a given value of income. In other words, I am saying that on average, let me emphasize on the term average once again. On average, if a family is earning $80, then on average it is consuming $65. Similarly, for a family earning $100, generally or on average they are consuming $77. So this particular column, the first column, may be called the first subpopulation. Then the second column, this may be called the second subpopulation. So that is why you see the statement here that we have 10 subpopulations of Y or consumption, right? So these conditional mean or conditional expectation, this is the primary or pivotal point in which we are interested. That is, we are interested in estimating the conditional expectations or the average value of the Y variable for a given value of X. Okay, so let me further explain the concept with the help of this diagram. If I refer back to this table, you can see that against income level of 80, the average consumption is 65. Now come back to the diagram. You see, if the income is 80, this solid or the dot here in the center, the thick dot you could say with a more volume, this is the conditional expectation 65. Whereas the other dots, you see the smaller dots here, they represent these values 55, 60, 65, 70 and 75, right? So what does that mean? This diagram shows that the population regression line or the population regression function is simply conjoining or joining all the values of conditional means of the dependent variable, that is in this case income, for a given value of the dependent variable which is consumption for a given value of income. So population regression function, it's actually what you are looking at. Why am I calling this population regression function? Because this is showing all the dots or the full possible data. You see, this full table is all possible, the 60 complete families in a neighborhood. So this is population regression function. Now if I say that what are the conditional probabilities for a particular family, coming back to the table, if you look at this 55, what's the probability that a family who is earning $80 consumes 55, right? I repeat the question, what's the probability that a family who's earning $80 consumes 55 dollars? So you could see that these are 5 values. So this 55 is just one value. So 1 divided by 5. So 1 by 5 is the chance that the family will consume $55. Again, 1 by 5 is the chance that the family will consume $60, and so on. So that's why we have, in other words, each of the value is equally likely. So why I am suddenly discussing the conditional probabilities is because I'll introduce the concept of these distributions here. So if this is the population regression line, once again, if this is the population regression line, if on these dots I superimpose a bell shape like here, although here you see only 3 bells, but you can draw, coming back to this diagram, you can draw the bell shapes on all of these, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can have 10 bells, but just for the sake of clear view, I'm showing here 3 bell shapes. And why in particular bell shape? Because there is one underlying assumption that the regression generally works well, or the ordinary least square regression works well when this distribution is normal, and you know that normal distribution is bell shaped. So this is an alternative display of the population regression line. Okay, so coming back to the concept of conditional expectation, that is the expected or the predicted value of the dependent variable for a given value of the independent variable. So we can also write that this conditional expectation depends upon the value of x. That's why we have written that this conditional expectation is a function of x, right? So we can call this equation as conditional expectation function, or the population regression function, or simply population regression. So these are alternative terminologies that you may come across. That's why I'm telling you that all of these are used alternatively. Okay. Now the population regression function, or the conditional regression function, or the conditional expectation function, this function, in this form, this is just a general expression. But what if I write that this conditional expectation, okay, it's a function of x, but what type of function? If I say that it's of this form, beta 1, which is a constant or a parameter, plus beta 2, another parameter, times xi. That is, beta 1 and beta 2 are regression coefficients, right? Xi is your independent variable. So if I say that, relating back, if my dependent variable was consumption, so expected consumption for a given value of income is equal to some constant plus another constant multiplied by the value of income, right? So now you can see that this is a linear expression. So that's why I've called it the linear population regression function. I'll also come in detail that why only this type of form is linear, or all there other alternative forms that you can call linear. So proceeding further, let me introduce another example. Suppose we have data on the average SAT scores, and those of you who know about the SAT score, they know that SAT is an aptitude test which grades students on 3 dimensions, that is reading, mathematics and writing. And let's say this data is about this much students, some 947,347 students taking the SAT exam in 2007. Okay, like we have data of all the students who took the SAT exam in 2007. So based on this diagram, what you can see is actually this, you see this label or the axis, that is the x-axis, should have been labeled. This is actually income level, right? So we have data on income level, whereas on y-axis we have data on average math score in the SAT exam. So what, for example, we have actual data and we plotted it on a scatter plot, and we saw that it's an upward sloping line. So what does that mean? It means that generally whenever there is an increase in income, it is expected that math score increases. In other words, we are saying that we are expecting that the families who are earning more, the students who belong to the families who are earning more are scoring more in mathematics. So let me give further explanation. So first of all, even if the diagram says that there seems to be a positive relationship between income and math score in the SAT test, you won't say that it is a cause or a reason. Income is not a cause of a higher score in the math section of SAT. There may be further other reasons. There may be other causes. We can only say that they are positively and strongly related, but we can't say that income is the cause of a higher math score in the SAT exam, because actual cause may be that those families who are earning higher, they can afford to provide private tuitions, for example, to their offsprings, that is, the students who belong to a well-off family may be using services of a private tutor. So there may be, you can build alternative discourses that what is the reason for higher math score for the families that are earning higher, right? Okay, so we were discussing the concept of linear regression. So what is meant by a linear regression? Let me introduce it formally. Linear regression will always mean a regression that is linear in the parameters, that is the betas, that is the power of betas or the exponent of beta is always 1, right? In the regression connotation, we say a model is linear whenever it is linear in the parameters. No matter if the variables have any non-linear behavior, that doesn't matter. Let me explain this further with the help of, before I refer to this diagram. Let's come to the later part of the discussion. I know this is a little bit disturbance on your part that I'm changing slides so frequently, but just trying to provide you with the relevant and important information. Okay, so we were discussing that when a model is linear, it means that the parameter have power 1. If you look at this equation, y is equal to beta 1 plus beta 2 times x square, you can see that x has a power of 2, but x is a variable, so it doesn't matter. As we said that whenever beta have power 1, we will be declare it linear in regression setup. But if beta has power other than 1, right? For example, if we have this equation where beta 2 is in square form, then this will be declared non-linear, right? Okay, so by looking at the table given below, I won't read all the cells, but for example, if there is a model which is linear in parameter and it's linear in variables, that is, all the variables have power 1, all the parameters have power 1, of course it is linear. Similarly, if you read at the second entry here, if the model is not linear in parameters, that is, the parameters are raised to power other than 1, just like this equation, the second equation that we discussed here, so then this will be non-linear regression model. And similarly, other cells you can easily interpret. So this was about when to call an equation as linear regression and when to call it non-linear. So let's proceed further. Coming back to the example of consumption and the income. So, and by the way, for your convenience, this image is displayed here again for your convenience. So given the income level of xi, that is, given the income level for someone with a consumption value, let me restate. Given the income level equal to xi, what are these xi's like 80, 100, 120, so on. So given the income level of xi, an individual family's consumption expenditure is clustered around the average consumption of all families. So don't get afraid of this seemingly technical or you can say verbose type of explanation. Just look at that diagram once again, the population regression function, this particular diagram. You see this particular solid line or the conditional expectation, you can see that the smaller dots, you can say that these are all clustered around this big dot, which is the conditional expectation, right? So this is what is being said here. Coming back to this type of explanation, right? So given the income level, an individual's family's consumption is clustered around the average consumption or the conditional expectation, right? So that's what we are saying. If you look at what is meant by clustered around, it means that, for example, if you are a particular family who is consuming $55, whereas the population regression function says that your expected consumption should be 65. That means your conditional expectation is 65. That is, the model will predict that you will you will consume $65, but actually you won't be consuming 65. You may be one of that family which is actually consuming 55. So that is why we have added a term UI, which means that each actual value of consumption is equal to estimated or the predicted value of consumption plus the random error part, or plus the deviation between the actual consumption value and the conditional or the expected consumption value, right? So that's why I have written the same regression model in the form of this you can say dichotomy. And why dichotomy? Because there are two terms here. The first one is the conditional expectation, and the second one is the random error or the stochastic error term. Stochastic is nothing, it simply means something that is random. Okay, so random error is often called stochastic disturbance term or residual term as well, because you may come across alternative type of terminology in the textbook. So I think it's my responsibility to acquaint you with equivalent terms for random error, which I said it could be called disturbance term, it could be called residual term, right? Or it may even be called the unexplained part, right? Because this is the unexplained variation in consumption, right? Okay, so some of the books or some of the explanation call this conditional expectation as y hat, right? Y hat means simply predicted value of y or predicted value of consumption for a given value of income. Okay, so as I said, this conditional expectation part is simply the average or the mean consumption expenditure of all the families with the same level of income, right? That is, for example, coming back to this figure again, let's say if this conditional expectation is 65 for a given value of x, that is for a given value of 80. So what does that mean? Just try to think out loud, try to interpret it. So it means that if you are earning 80 on average, or a predicted consumption will be 65. So that's why we are saying that all these families, that whatever fall in this cluster in the income range of 80, their average consumption or their expected consumption will be 65. So that's why we are saying that this is simply the average consumption expenditure of the families with the same level of income. So coming back, this 65 conditional expectation is only applicable for families earning $80. So that's why it's written here that same level of income, and then this is applicable. Second, the UI or the random error part, we just introduced that the random error part is because of the change in actual value of y versus the average or the expected value of y. This will be further explained when you dig further in the concept of linear regression. Okay, now although it's pretty much clear from here, even from this table, that the actual consumption values are different and the conditional expectation or the predicted value of the consumption are different. So, but now introduce it practically, or you can say a prudent justification that why we include the random error or this UI part in the regression function. So there are a variety of reasons. It's actually a proxy for different type of factors that collectively justify that you cannot predict things with 100% accuracy. In other words, in a very simple way, if I relate back to the consumption and income example, it simply means that I can never predict the you can say I can never predict the exact value of consumption, right? I can say that this is the expected value. I mean, because once you, if you are a student of economics, you must have studied the consumer behavior theories, and you can, even if you haven't studied, but you can easily think that people consume due. I mean, people's consumption pattern are not totally dependent upon income. There are variety of other factors that explain what are your consumption patterns. So coming back, why we introduce the random error part, the first factor is the vagueness of the theory. For example, as I said, that we have data on consumption and income, but what about the other factors? For example, let me introduce one example. We are two families. Suppose we have two families, and they both are earning the same level of income, right? Both families are earning same level of income, but it is fairly possible that their consumption levels are entirely different, and there may be numerous reasons behind it, that why they are consuming different. It depends upon so many things. I mean, we can never assume that human beings are going to behave in a fixed pattern. It's fairly possible that in one of the family there are people who believe in enjoying the present. They believe in the phenomena that there is no point in saving and one should enjoy the current time one has, whereas the other family has a tendency of future planning, so they save more, and that's why their consumption patterns are different. So you see, there may be vagueness in the theory, that the theory is only reflecting upon income and consumption, but actually consumption is dependent upon many other things that are not included in your model. And sometimes the other factor is the unavailability of data. Sometimes you know that there are other things that can influence your dependent variable. That is, you can say that, for example, what is a particular approach of a family towards life. For example, does a family potentially give weight to living in the present, enjoying the current moments, or does a family is future oriented and it tends to plan that how to save more for future. But we can't have on this type of structured data. For example, if my interest is to predict the consumption pattern of the people living in city, let's say Islamabad, but it's possible that I have data on consumption and income of all the people living in Islamabad, but I don't have data on these behavioral aspects. How do they approach toward life? They live in present, or they give more weight to their future planning. So sometimes there are things that can explain the dependent variable, but you don't have data on them. So the random error term is actually also introduced because if you don't have data on some variables, it's stored in the random error part. For example, you don't have data on how a family has a particular approach toward life, then that behavioral aspect is stored in the random error part. If the theory is vague, then that influence of a vague theory, it is loaded in the random error part. Then next is core variable versus peripheral variables. So let's explain through another example. Let's say again consumption income example, but we know that other than income, it matters that what are the number of children, what is the number of children in a family, let's say x2, what is the, for example, gender of the head of the household who is taking consumption decisions for the entire family, And maybe there are studies that even say that it matters to which religion you belong, your consumption style depends upon your religion as well. What's your education level, in which area you are living. So there are countless other factors or the countless other variables that can explain what is your consumption style. But of course, you have to apply a limit or an end on the model somewhere. Of course, you can't just keep on collecting data on all of these variables, and then there is no end, because you keep on exploring literature and you will find countless variables. But you have to decide that up till which level I have to take this research inquiry. What are my core study variables? Am I interested in exploring the relationship between consumption and income? And so that's the end, or should I include peripheral or you can say secondary variables as well in the model, right? But sometimes if I don't include these secondary variables, actually I'm just saying that these secondary variables are not that much important. You can say that, let's say, a major part of your consumption decision are decided on the basis of your income. So and maybe a behavioral psychologist may disagree with this, but as a student of economics, you can really understand this phenomenon that consumption depends upon income. So what about these other variables? Okay, these are also related to your consumption pattern, but these are not the core variables, so their joint impact will be stored in the random error or the residual part or the UI part. Let me show once again this UI part, right? So the peripheral variables, their joint impact will be stored in the random error part. Then even if we have, okay, let's say we have data on, suppose, many variables, and we say that we have, coming back to this example, even in this case, suppose if somehow I include the complete data on number of children, on gender of the head of the household, religion, education, and so on. Let's say I have well structured data on all these variables as well. Even then I can never predict the consumption pattern with 100% accuracy, because remember, we are dealing with human behavior and there is an intrinsic randomness in human being, right? Even if we introduce all the relevant variables in the model, even then there may be a particular family that is behaving in a different way. I mean, even if you have data on all the important variables and you put in the values of all those variables, even then you will not be able to calculate consumption. I repeatedly use this word, that calculation is not a you can say something in which regression is pivoting on. Regression is pivoting or focused on estimation, right? So there is intrinsic randomness in human beings, so that's why random error is also a proxy for intrinsic randomness in human behaviors, right? Okay, another factor may be that sometimes we don't have data on some variable and we try to proxy them, and that the fact that we are not using the actual variables but the proxy variables, that also introduces a sort of inaccuracy or random error part in the model. For example, Friedman's theory of consumption function, if you refer back, and if you're not aware of it, it's highly advisable that you pause the lecture and go and have a quick recap of what's the Friedman theory of consumption function. So this theory relates permanent consumption as a function of permanent income. That is, this theory says that permanent consumption depends upon permanent income. But you see, in real life, whenever we have income figures, we don't have data on permanent income and permanent consumption. We only have data on current consumption, current income, right? So that means if I proxy permanent consumption by current consumption and permanent income by current income, then we are not using the actual variables, right? We are using proxy variables. So because of using these proxy variables, again, we won't be able to predict things with 100% accuracy. And once again, here comes the significance of the random error or the stochastic disturbance term UI. Okay, one more factor because of which we introduce the random error in the model is, you can say, let's keep things lighter. This principle of parsimony is simply that you try to be modest. So actually the model at hand is trying to be simple. Parsimony simply means simple. So we like to keep our regression model as simple as possible. It means, you see, we want to keep things simple. Why? Because so that we can interpret them easily. Multiple people can easily use the model. So why to use a very complicated and fancy model and try to increase the efficiency of the model? There is a trade-off. Actually, if you make the model more and more complex, it means that you are limiting your target audience. Very few people will be able to understand a complex model. So if you keep the model simple, it means even if the actual relationship between consumption and income is a complicated function, but you have used simple linear function. Which linear function? Beta 1 plus beta 2x, right? So using the principle of parsimony, or you try to include only those variables in the model which are highly or significantly related to your dependent variable, and you try to keep the model's functional form as simple as possible. So when you try to do these things, you are actually intentionally compromising on some of the variables. You are intentionally compromising on the functional form of the model, and consequently it means that you are once again not predicting the y variable with 100% accuracy. You are predicting it with, let's say, hypothetically speaking, let's say 88% accuracy. So later on we will also study a different criterion with the help of which we decide that how can we state that a parsimonious or a simple model is simple yet efficient as well. So we will discuss later in the course the concept of R square and the concept of regression, standard error of regression, which will show the predictive power of a model. So actually what I am trying to say here, that the end goal is to increase the efficiency of the model, that is, increase the R square and decrease the standard error of regression, but we are also trying to keep the model as simple as possible, right? So this is a sort of constrained optimization. Okay, then coming back to why we introduced the random error term. I hope by now you have clear sort of a mind map that why we include the random error part in the model. But another factor is the wrong functional form. Suppose we know that if this y is consumption and this x is income, suppose hypothetically speaking you say that you know that the actual relationship between consumption and income is given by the second equation. Suppose Of course, I'm not assuming that just by looking at the data you can understand that which type of relationship is a suitable fit to that model. Let's say where you can say advanced stage of econometrics concept. For now, let's say I'm just stating, suppose this is the correct relationship. This is how the income and consumption are related, but you try to fit this model, right? The first one, you try to approximate the second model with the help of the first one. So what has happened that you have used the wrong functional form, that is the actual functional form is this, but you have used the first one. So by using the wrong functional form, you know, the random error will also contain the impact if you have used a wrong functional form of the relationship between the dependent variable and the independent variable. Okay, so by now it's quite clear in your mind that population regression function, just for a quick recap, coming back to where we started the whole debate, that is the population regression function. So this data where we were discussing about 60 families. So this is data of all possible families in a community, and that's why we call it population, not sample. But what if I take a random sample of some families from this table, that is out of the 60 families living in that community, I take a random sample of some families, which I will show here shortly. Just a moment, and see, so for your convenience, that data of 60 families I have shown here once again. So this was population data. So it's possible that I take a random sample, for example, so for the family earning 80, the randomly selected value is 70, or the family earning 100, the randomly selected value is 65, and so on. So actually I am randomly taking one observation from each column. So that is actually one random sample, because in reality you won't have data of all the families, because remember that in statistics you always, or generally, you have data on random samples. So you will have pair of dependent variable and independent variable. So this is one possible random sample, but it is also possible that this random sample may be selected. That is, against 80 you may choose a family with 55 consumption value. Again, similarly, against income of 100, you may choose a family consuming $88. From this column you can see the last value is 88. So you see, you can have different random samples. So if I introduce, you can see what is SRF. It is sample regression function. So SRF1 maybe, if I take all these values, this the first sample, this y and x, if I plot only these 70 against 80, 65 against 100 and so on, then I'll have SRF1, sample regression function 1. Similarly, if I plot these pair of observations, then I will get SRF2, or the sample regression function 2. So why am I discussing? Because remember that sample regression function, you can say that it's a random variable. Why it's random? This line changes. As soon as you change the random sample, the sample regression function will change, right? So unlike population regression function, pardon me for repeatedly going back to the population regression function slide, but I want to make sure that the audience are able to understand things efficiently. If you look at the population regression function, this straight line is, you can say, fixed. That is, for this complete population of 60 families, this is the only possible way population regression function will be drawn, because it is actually conjoining the average values. So average is going to be here. Similarly, in other words, it's this average value can't be here. Of course, average will be somewhere in the center. So these averages are fixed, and so population regression function has a fixed pattern. But the sample regression function, you see, if the sample changes, coming back to the slide having the data, you see, if the sample changes, so does the SRF. As sample regression function 1 and 2, they are different because they are coming out of different samples. However, remember that in practice we don't have data on 2 random samples. That is, generally we may be having data on only this particular form, so we will be having only SRF1. But this discussion is to let you understand that the sample regression function is a random variable. Okay, so that means that population regression function, from where we started the discussion, if I apply, okay, let me say, if this equation is without these hats, right? If this equation is without these hats, that means that I have actual data on y, actual data on x, and full possible data, then that is population regression function. But if I apply hat on betas, that means that they are coming out of a random sample. Let me try to further explain it. If, for example, I have SRF1, sample regression function 1, then it means that the beta coming out of sample regression function 1 will be an estimate of the actual beta had I run the regression on the full population. Coming back to the diagram again, if I for example, if I run regression on the all 60 observations, then the beta that I will get will be actual beta. But you know that in practice we don't analyze full population, because if we are analyzing full population, then what's the point of random sampling? What's the point of using minimum data to give maximum policy recommendation? So just a second, let me go back. So the betas estimated from the sample regression function, they are an estimate of betas in the population. So beta 1 hat is an estimate of beta 1, or to put it very simple words, sample regression function is an estimate of population regression function, right? So we can express the sample regression function as follows. That is, if I switch back or refer back to the consumption and income example, this sample regression function says that the consumption of a family is equal to beta 1 hat plus beta 2 hat times its income plus the random error part. And you see, we even have a hat on the random error. Why? Because once again, this UI hat is an estimate of UI in the population. That is, this is actually population regression function. That is, if I use the data on full 60 families, then the regression equation will be this. But we want to use minimum data to give a very fair approximation of this population regression function. So instead of using data of 60 families, I'll be using data of selected families. As you see, for example, here you see how many are they. Let's count: 1 2 3 4 5 6 7 8 9 10. So instead of using 60 pairs in the population, if I'm using only these 10 pairs, but still my findings are generalizable for those 60 families, then what happened? I have used less data, that is, I have put in lesser effort, but still my estimates or my results are generalizable for the 60 families in the population. So sample regression function is a fair approximation of the population regression function. So next, as I mentioned earlier in the video, that I'm going to explain with the help of some models that what type of equations are declared as linear regression models. So this equation, actually this 2.7 means this is question number 2.7 from the Gujarati and Porter book, which I mentioned in the start of the video. So question says that we have to decide whether these models are linear, and we also have to tell the reason. So if you look at this A equation, if I simply take the log of this equation, if you don't know about the log function, kindly pause the video and go and refresh your concepts about the log function. So if I take the log on both sides, then you know that this e or the exponential function and the log function are inverse of each other. Okay, so if I take log on both sides, this will become log of y is equal to if it's written here as well, so log or ln, that is the natural log. So I can apply natural log on both sides, and the exponential function and the ln function, they are inverse functions, so they cancel out, and I get ln of yi is equal to this. So now you see in this form the betas have power 1, so this becomes a linear regression model. Now if you look at equation B, this can be easily transformed into a linear model. So how? Let me show the derivation of part B. Have a look again at this part B. So let me derive. So this is the actual equation. Yi is equal to 1 over 1 plus exponential function of this thing. So if I want to make it linear, suppose I reciprocate this, so I get 1 over yi is equal to, so the reciprocal of this becomes this 1 plus exponential of the entire thing, and then this 1 shifts here on the left side, so this becomes. So now it's quite easy if you just let this derivation absorb. Maybe you pause the video and it's very easily understandable that the end form becomes linear, because once again the betas are raised to the power 1 only. So this is again a linear regression function. That's why part B it is written that this model becomes a linear regression model. Now coming to, let's say, D. Even if you apply log on this model, you can try that this will never turn into a linear model. That is, you cannot, you see beta 1 is here as well, and then here it is also in the exponential function, so it's a complicated type of a model and you cannot easily linearize it, so it's a non-linear regression model. Okay, so next, just to further strengthen your concept, what is meant by an intrinsically linear regression model? And if the beta in the previous exercise part D was 0.8, beta 2 actually, would it be linear? First of all, there are actually two parts of this question. First, what is meant by an intrinsically linear regression model? So a linear regression model or an intrinsic linear regression model is a one that can be made linear, right? That is, if you were discussing here this part B, in actual form it seems non-linear, but this is intrinsically linear, because you see, with the help of these simple derivation you can easily linearize it. So intrinsically linear regression model means that you can make it linear with the help of some minor adjustments. The second part of the question is that if the beta 2 in part D is 0.8, going back to part D, so this is part D. If beta 2 is 0.8, right? If this beta 2 is 0.8, it's no longer here in the power of exponential function. And then again you can easily check that you can easily make it a linear, because this number beta 2 will be now a number, a constant, so you can easily apply the log now, right? So this will become linear regression model, right? Okay, now we have different once again another practical example. I won't again repeat the same explanation. The answers are here. It's highly advisable that those who are watching the video give it a try, and let's see if you are able to understand why these each part, whether they are linear or not. Although the answer is here as well, but you pause the video, give yourself a try whether you are able to decide whether these are linear or not. Okay, so next we have another example in which we see data on growth rate of real manufacturing wages and export, and the data are for 50 developing countries, right? First question is, what general conclusion do you draw from this diagram, right? So let's focus on the answer to this. What general conclusion do you draw from this diagram? So if you look at the diagram, what is it saying? That actually it's the change in export to GNP ratio, that is on the x-axis. I have the average value of change in export to GNP ratio, whereas on y-axis I have average growth in real manufacturing wages per year. So what's it saying? That overall there is a positive relationship between growth in real manufacturing wages and the growth in export to GNP ratio. So what does that mean? It shows that more export oriented countries have more growth in real wages. Why? Both are moving in same direction. The line is upward sloping. So the scatter diagram shows that more export oriented countries have more growth in real wages than less export oriented countries. Then the second part of the question is the regression line sketched in the diagram a population regression line or a sample regression line? If you look at the description, this data is only for 50 developing countries. It is not for the entire countries of the world. So of course this is a random sample. That's why you can say that it is a sample regression line. This is not a population regression line. Okay, next we have another question. By the way, I respect the fact that this video is relatively quite lengthy, so maybe you can pause it, just relax and then start the video again. So we have a scatter diagram given in this figure 2.9, and what type of data we have? We have, you see, on the x-axis, one title or one heading here is that these are the countries who have abundant land but less skilled workers. That is, These are the countries who have comparative advantage in land, but they are not advantaged in terms of skilled workers. So then there are some countries who have more skilled workers, that is, they have comparative advantage in labor. So what's happening is in this diagram, it's actually, if you look at this label, the countries that have abundant land but less skilled worker, they are producing more raw materials, right? This is a typical problem, that if you don't have skilled human capital stock, or you don't have skilled labor, then you end up producing more of the raw material. Whereas the countries which have more skilled workers but scarce land, they are producing more finished good or manufactured products instead of raw materials. So even if you don't know the name, but let me provide you, according to the well-known Hexerolin model of trade, countries tend to export goods whose production makes intensive use of their abundant factors of production. So this is what I was trying to explain a bit earlier. So in other words, if you are able to use the typical terminology of trade, in other words, this model emphasizes the relationship between factor endowments and comparative advantage. That is, the countries who have comparative advantage in skilled worker, they are producing manufactured products. The countries which have comparative advantage in land, they are producing or they are expected to produce more raw material, right? So this was about this particular example. Now I'm not going to discuss this example, the complete narrative for it, because you have the diagram here and I have shown the complete explanation here as well. So what I'm expecting from the audience that is watching this video is pause the video, give yourself a bit of time, look at this scatter diagram and see if you can understand the explanation which is written here, because these are actually different exercises, so it's not necessary that I cover all the exercises in the video as well. Okay, so I think we stop here, because this is quite you can say fully loaded sort of a lecture. We will continue from here in the next video. What I want to share here, pardon for a moment, but I want to show you something. Okay, so on a very serious note, thank you for watching Rao Hub's video, that's this channel name, and just a humble request that keep watching the videos and kindly support the channel, subscribe it and share it with relevant groups in your social circle. And if you wish to reach me, that is the instructor Dr. Aisha Nazuk, if you want to reach me, I have mentioned both my personal and my official email ID here, so you are more than welcome. If you want to have further clarity, you want to request for some course material or any other sort of collaboration, you are more than welcome to drop me an email. So thank you once again and hope to see you soon in the next video.